Hello everyone, welcome to Engineered Learnings. Engineered Learnings has been created as an effort to help and reach out to all the engineering students, aspirants and professionals out there with the basic understanding and the crux of the topics important for placements, vivas, semesters, competitive examinations and all types of interviews. So let's go to today's topic. Hello everyone, welcome to today's topic. Today we are going to discuss about another core technical topic, boundary layer development. Extremely important in terms of fluid mechanics, particularly for the mechanical engineering and the chemical engineering department. When I was in my BE course, our curriculum also had boundary layer development, but I personally struggled with it a lot, and I know how students struggle to understand the concept of boundary layer development. They get lost amidst the difficult and the complex numerical calculations of the boundary layer development, but actually the concept of boundary layer development is quite simple, and if you can crack the concept of boundary layer development, then it's going to be easy to deal with momentum transfer, mass transfer and heat transfer. Any practical mechanics problem will be easier to deal with or easier to visualize if we understand the concept of boundary layer development. So today we are going to try to understand the concept of boundary layer development with the help of classical mechanics. Yes, you heard it correct. Classical mechanics, class 12 mechanics, Newtonian mechanics, combined with a few concepts of fluid mechanics. We are going to try to ease the understanding of this boundary layer development. We are going to actually physically visualize this. So coming straight away to the topic, to understand the concept of boundary layer development, you need to first get the point that boundary layer development is of three types: momentum transfer boundary layer development, momentum mass transfer boundary layer development, mass, and heat transfer boundary layer development. Heat, momentum, mass and heat, all three boundary layer developments occur whenever there is a driving force. There is a difference. Momentum transfer occurs when there is difference between velocities, difference between momentums of two particular bodies. That is, there is a relative motion between the two. One is moving, one is stationary, and the two comes in contact with each other and a boundary layer develops. Momentum transfer boundary layer. Mass transfer occurs when there is a concentration gradient or mole fraction gradient. That is, supposedly a salt slab has a high concentration of salt, whereas pure water have no salt. So there is a mass transfer driving force or mass transfer gradient. So there a momentary mass transfer boundary layer development will occur. Heat transfer boundary layer occurs when there is a temperature gradient. That is, there is a heat transfer gradient or driving force. That is the particular body at a higher temperature and a particular body at a lower temperature comes in contact with each other. Then there is a temperature profile that develops and the boundary layer development is there. Heat transfer boundary layer development. So by the concept of the three, we can get that whenever there is a driving force, whenever there is a difference between two entities, there is a relative motion or there is a relative concentration, higher concentration, there is a relative higher temperature between the two bodies, there is a development of boundary layer. So we are going to try to understand the concept of momentum boundary layer. Mass and heat transfer boundary layer are analogous to momentum transfer boundary layer. Once we understand the concept of boundary layer development, then momentum transfer boundary layer development, similar will be the mass transfer boundary layer development and heat transfer boundary layer development. Why we are taking this momentum transfer boundary layer in particular? Because it's easier to visualize, because momentum is something to do with velocity, with motion. Mass transfer and heat transfer are something that is difficult to visualize. That concentration and diffusion is taking place between two bodies. It's difficult to visualize. Also, heat transfer, you cannot physically see it, but momentum you can physically measure, you can physically see, you can physically visualize that. So it's easier to visualize momentum transfer. That's why we are taking that one example of momentum transfer boundary layer development. So straight away going to momentum transfer boundary layer development, as I have already drawn it here. You can see there is a stationary block. There is a stationary block kept here and a gush of water is coming at a velocity of u infinity. Average velocity of u infinity. So every layer of water is having a velocity of u infinity. Now it strikes the block. Now understand one thing. You know class 12 physics that there will be a friction, there is an opposing force when a stationary body, supposedly this is the stationary body and the moving body meets the stationary body. The stationary body will try to oppose the motion of the moving body and will hence create a restricting force, creating a negative acceleration. Negative acceleration, as we already we know that when we apply the brakes of a car engine, it creates friction and that adds on to a negative acceleration opposite to the motion of the body, restricting its motion. So there is a negative force that acts when a moving body meets a stationary body due to friction. So we have to understand, we have to take just this concept to understand the boundary layer development. There is nothing more to it. So if I straight away like go for this problem, so what happens is when this layer comes in contact, in layers above this block, what happens is the first layer of liquid that meets the block is at no slip. So no slip condition tells me that the layer common to the stationary object, to body 1 and body 2, will be at same velocity. It will share the same shear stress, it will share the same properties, and it will have the same velocity. So since my block is stationary, so the first layer of liquid that comes in contact with the block will also be stationary. So V is equals to 0 for the first layer of liquid, and as we proceed a little higher up, the velocity will keep on increasing because the shear stress or the frictional force keeps on decreasing layers after layers. When we drop a bucket of water, you will see that the top layer moves at a higher velocity and the layer corresponding to the bottom faces a frictional force and there is a restriction. So that restriction creates a negative acceleration and decreases the velocity. So this is the concept of it all. So if I consider like a surface only, this is the 3-dimensional figure. If I take it to be a 2-dimensional figure, understand the concept. Maintaining a no slip condition, we take a 2-dimensional figure supposedly. This is what is happening. This is my y-axis supposedly, and this is my x-axis supposedly, and this is my block. This is my fluid that is coming in layers. This is my first layer. So V is equals to 0 at this layer. Then V is something. As we go up, V also is increasing in the upward direction. So there is a positive dVx. So if we consider this as the Vx, since it is in x direction, dVx dy, that is the rate of change of velocity in the y direction, is actually positive. So there is a positive rate of change of velocity in the y direction, and the velocity increases as we move layers up from the stationary block, because we understand the friction is going to be decreased in layers. And finally what happens is, if this was coming at u infinity, this layer will not be, supposedly we are considering a straight chain, that is the y coordinate we are considering to be same. So at this point and at this point, at these 2 points, the velocities are not going to be same, because the frictional force or the shear stress actually creates a negative acceleration which decreases the velocity. So if the y is fixed at a fixed y, at a particular y, Vx will not be same at different x. What does this mean? This means that at this point of time, supposedly this is x1 coordinate of x-axis and this is y1 coordinate of y-axis. This remains as y1 coordinate of y-axis, but this becomes x2 coordinate of x-axis. So at x1 and at x2, that is Vx1 will not be equal to Vx2. In fact, Vx2, to be more specific, Vx2 will be less than Vx1 because of the negative acceleration. Because the plate is giving some negative force on the motion of the liquid. So we are seeing that there is in the x direction dVx dx in the x direction is not 0. That is, there is a change in velocity as we proceed in this direction. There is a change in velocity in this direction because the layers are like the friction along layers is decreasing, and also a change in velocity along this direction because of the friction. Now what happens? Very interestingly, you will have to understand that whenever there is a block, whenever there is a body, the negative acceleration, negative force that it provides is by the virtue of its shear stress. So shear stress into area is my negative force, Fn I am considering in the negative direction. The decelerating force, the deceleration that it provides is nothing but Fn by m, if m is my total mass of liquid. So Fn by m, because we know F is equals to ma, so the negative acceleration that the plate is providing to the fluid is nothing but F by m, and F is nothing but shear stress into area by m. Now here comes the concept of fluid mechanics. Here comes the concept of fluid mechanics. Now we know that tau is nothing but mu into dvx dy whole to the power n. For Newtonian fluid, n is equals to 1. For non-Newtonian, it can be less than 1 or greater than 1. In any of the cases, trust me, what happens is, irrespective of the value of n, this dvx dy, once it increases, tau is high. Tau is high if dvx dy is high. Tau is less if dvx dy is less. That is rate of change of velocity along the y direction. Now you have to understand, as the tau increases, the negative acceleration increases. That is, and as the tau decreases, negative acceleration decreases. That is, the negative acceleration to the motion of the fluid decreases as tau decreases. Now what is happening? Now let's understand the concept here. Supposedly the block surface is here, two-dimensional. The liquid is coming in. The liquid is interacting with the block. The block is providing a negative force of tau into A, where tau is equals to mu dvx dy into A. For Newtonian fluid, supposedly considering n to be 1. So mu dvx dy into A. So what happens is, immediately this becomes 0, this becomes supposedly 1, this becomes 2, this becomes u infinity, supposedly 5 meter per second. If it's coming at a speed of 5 meter per second, v is equals to 5 meter per second, free stream velocity. What is free stream velocity? When the stream hadn't met this stationary body, it was coming with the average velocity of each of the layers as 5 meter per second. It was moving at an average speed. As soon as it comes in contact with the boundary layer, what happens is, the immediate layer touching the slab becomes 0, then 1, then 2, then 3, then 4, and finally at a point of time it reaches 5. At this point of time it reaches 5. So what happens is, if you see the free stream velocity 5, and at this point of time these are not being two same y coordinates, along the x, their velocity is not same because of the frictional force, but they will be same at a certain point of time when the frictional force becomes less dominant, or when the frictional force becomes negligible. At that point of time, if we draw it at a certain point of time, at a certain y, this will be u infinity. So this will be u infinity. This will be something some profile coming from 0 to u infinity. Now, as we proceed further, what is happening? Now understand this concept. As we proceed further, this u infinity will further decrease, and it is not u infinity, it is 0.99 of u infinity. That is 99% of the free stream velocity it has reached at this point of time. And this is the height. Of the boundary layer. Above this, everything is 0.99 of u infinity. That is further, there is at this point after this point, there is the dvx dy is equals to 0. So the tau is equals to 0. There is no shear stress beyond this point is acting. So dvx dy becomes 0. Because mu cannot be 0, so dvx dy becomes 0 after this point of time, because tau becomes 0. That is, the shear stress or the frictional stress that was creating the negative deceleration was 0. Now what is happening? As we proceed from here to here, this 0.99 u infinity will not remain 0.99 u infinity, it will become 0.95 u infinity, and somewhere around this point it will become 0.99 u infinity. So what is happening is we are seeing that again at the same y along x there is a change in velocity. So 0.99, supposedly I have touched this. After the second layer, this is my 0.99 u infinity. For the third layer, this becomes 0.95 u infinity, and this becomes 0.99 u infinity. So there is a continuous gradual increase in the boundary layer height. There is a continuous gradual increase in the boundary layer height as we go along the x direction. So y becomes a function of x such that it is positive. With x, the y increases. That is, the boundary layer height increases. So what will happen is, that is, y becomes, the boundary layer height becomes a function of x. So as we go along x, the boundary layer height increases. So something like this will develop. Something like this will develop. This is u infinity for the first layer. For the second layer, this is my u infinity, because again it fetches friction. For the third layer, something like this, u infinity will be somewhere here. And my boundary layer is going to be slowly increasing. That is, the locus of this u infinity points is going to be something like this. So this is y and this is x. So y increases. The boundary layer thickness increases with x. Now comes the concept of initially developing motion and fully developed motion. So what happens is, after a certain x, this curve becomes flattened. That is, after a certain point of time, the u infinity is going to be the same throughout. That is, with x, there is no further change of dx. That is, dvx, dx is equals to 0. That is, supposedly the slab is coming in one time. So there's something like this. First u infinity is developing here, then u infinity is developing here, then u infinity is developing here, and then finally the u infinity keeps on developing at this position. So this is also u infinity, this is also u infinity, this is also u infinity. So at a particular y along x, there is no change in Vx. So dvx dx is equals to 0. That is when you call it. That is, this is the initially developing region, and this is fully developed. That is, the boundary layer has fully developed itself. There is no further scope of development. Now you may question that the friction will keep on occurring. There is always a negative acceleration and the u will keep on decreasing. Yes, it will. Yes, it will keep on decreasing. Supposedly there is a positive acceleration because of the force of the liquid that is coming in. Supposedly the force of the liquid is F. So F by m is my positive acceleration. And my negative acceleration is tau into a by m, as of already discussed. And my net acceleration is a negative minus a positive. Because there is a decrease in velocity, we can understand, because there is a decrease in velocity, this becomes 0.95 u infinity, this becomes 0.9 u infinity. So at the same point of y, the velocity is decreasing, so we can understand the negative acceleration is greater than the positive acceleration. An is greater than ap, so there is a net negative acceleration because of which the velocity is decreasing. So an minus ap is the net negative acceleration. Now this net negative acceleration at this point in the fully developed region will become 0. Then only this will become a constant velocity. When is the velocity constant? When is the velocity constant? When the acceleration is 0. So the negative acceleration minus the positive acceleration should be 0 in order to become constant. Now why is this negative acceleration? Because positive acceleration is same, it is constant. This negative acceleration is constantly decreasing along x. So an is decreasing as x is increasing. So along x, the negative acceleration provided by the plate is decreasing. Now what is the expression of the negative acceleration? It is nothing but tau into a by m, as we have already explained. Now a cannot change, m cannot change, tau can change. Remember this, guys. Now what we have discussed, tau is nothing but mu into dvx dy whole to the power n. Now if dvx dy decreases, tau decreases. Now macroscopically, what is dvx dy? That is the rate of change of velocity along the y direction, Now if we take this boundary layer development, supposedly this is the slab and this is my u infinity. This is the slab, this is my supposedly first u infinity, then this becomes my u infinity, here becomes my u infinity, then here becomes my u infinity, or 0.99 of u infinity. So what is happening? What is happening, my friends? You have to understand the concept of it now. For the first layer, macroscopically, this is my y, macroscopically dvx dy macroscopically becomes nothing but u infinity minus 0 by y, because this is 0, this is u infinity. The two velocities difference in the y direction divided by the distance y along which the difference takes place. So u infinity by y. Now for the second layer, since the velocity is decreased, the u infinity occurs a little higher because of the boundary layer development and the friction. So u infinity divided by y, what happens? This y increases. For the second layer, u infinity remains the same, but the y increases. Increase in y decreases the dvx dy. So what is happening is tau is decreasing in the process because of the decrease in dvx dy. That has occurred because of the increase of y, that is the boundary layer thickness, and hence what happens, the negative acceleration keeps on decreasing, and at a point of time ap is equals to a. And beyond that point dvx dy is 0. That is u infinity remains constant throughout the layers. So it is a fully developed region, and hence dvx dy is constant because the y doesn't change after that. Y remains the same throughout. Boundary layer thickness. The boundary layer thickness remains the same throughout, and then tau becomes the same, an remains the same, ap minus an is always 0 beyond the fully developed region. So ap is equals to a positive acceleration is equals to a negative acceleration. So what is happening? First of all, if we rub all of this concept and try to understand it in the basic terms, what is happening is there is a slab, the liquid is meeting the slab. The liquid layer immediate to the slab is facing a velocity of 0. It is reaching a velocity of u infinity, there is free stream velocity 0.99 of u infinity at a certain point of time, after a certain layer thickness y. As it proceeds, u infinity is reached further beyond. In the process, what happens is the first layer negative acceleration is greater than the second layer, so the negative acceleration keeps on decreasing as we move forward. So tau is the reason of decreasing velocity. The decreasing velocity is the reason of negative acceleration. So firstly, tau causes decrease in velocity. The decrease in velocity causes u infinity to occur at a higher y. Because of the decrease in velocity, the free stream velocity is achieved at a higher height. So y increases. Due to the increase in y, as a result of y increase in the second layer rather than the first layer, the u infinity development, since the increase in y is occurring, the negative acceleration decreases. In the process, negative acceleration decrease causes a decrease in the negative an is decreasing. So this will be dvx dy decreases, and hence tau decreases. So tau itself in the first layer is a reason of tau decrease in the second layer. So tau constantly keeps on decreasing, and at a certain point of time, fully developed region, in the fully developed region, tau constant. when tau is constant, acceleration a p minus a n, effective acceleration a effective is equals to 0. That is dvx dx is equals to 0. But dvx dy definitely exists positively till a certain point, beyond which dvx dy in this region is existent, but beyond this region, in this region, beyond 0.99 u infinity, dvx dy as explained is also 0. So the shear stress is 0. So you see that in the initially developing region, tau in the initially developing region, supposedly this, tau is decreasing constantly. In the fully developed region, tau is constant. In the initial region, dvx dx is not equal to 0. In the fully developed region, dvx dx is equals to 0. This is the concept of fully developed and initially developing region and the boundary layer development. What is the boundary layer development? This is my boundary layer development. This is the locus connected of all the points. And what is happening is there is a boundary layer development beyond which the free stream velocity is achieved. So in stages you face friction and you don't move with the same velocity that we came with. We are moving with a very high speed velocity when we do not face any interaction. Once we face the interaction, once we face the restriction from a negative acceleration from a block, our velocity decreases and we achieve the free stream at a height. As we proceed further negative acceleration, and we achieve the free stream velocity at a greater height. As we proceed further negative acceleration, that is deceleration, with the same positive acceleration, we achieve the free stream velocity at a further greater height. So the boundary layer thickness is a function of x. As the x increases, the boundary layer thickness increases. But beyond a certain point, beyond the initially developed region, with x, the boundary layer thickness doesn't increase. So the y doesn't increase with x in the fully developed region, fully developed. Y is only a function of x in the developing region, but once it is fully developed, with increase in x, the boundary layer thickness remains the same. That is, here also the free stream velocity is this, there also the free stream velocity is this. This is because my positive acceleration is matching my negative acceleration. Because my negative acceleration initially is very high, but as we move on in the x direction, an keeps on decreasing, negative acceleration keeps on decreasing, and finally it matches positive acceleration and my stream moves with a constant velocity profile along y direction. That is, whatever is the velocity at a particular y, whatever is the velocity at this point at a particular y, it will remain the same along x. This is the fully developed region. So this is the boundary layer concept, that is a layer developing with different velocities in stages, reaching a free stream velocity after a certain height, and that height is my boundary layer thickness. So this is the concept of momentum transfer boundary layer. Similar is the mass transfer boundary layer and the heat transfer boundary layer. To understand the concepts of the mass transfer and heat transfer boundary layer, we can draw analogs to momentum transfer boundary layer. Now this is a question that was asked in Bhel to me, that give a situation where three types of boundary layer exists. Now I am going to interestingly discuss that. There is a slab, a salt slab lying in a seawater, and the seawater is coming. So what happens is there is a concentration gradient and the slab is at a high temperature. Slab is at a higher temperature. Here the temperature is low, the concentration is low, the concentration is high. Here the velocity is 0, here the velocity is infinity. So there are gradient of all three types. A salt slab at a higher temperature is lying in a sea of water. So what happens is there is a boundary layer development like this of the momentum transfer. There is a boundary layer development of this type. T infinity supposedly is coming with, T infinity is lesser than T. So it will be something like this, T slab. And for concentration also it will be something like this. Concentration of slab, concentration infinity, decreasing as we proceed. So this is the concept of it all. slab having a higher concentration, so the immediate layer of water will also have this concentration, and it will gradually decrease as we proceed further. And these are the three, all coincided here. I've just drawn it for reference at different regions, but they're all coincided to this particular point. And as we proceed, this T infinity, C infinity, and U infinity, development height will increase. So it will be something like this. So this is the concept of existing, three conditions existing simultaneously: heat transfer boundary layer, mass transfer boundary layer, and momentum transfer boundary layer. A salt slab, stationary salt slab at a higher temperature lying in a seawater. So there is a concentration gradient, there is a temperature gradient, there is a momentum transfer, there is velocity or momentum gradient as well. So this is the example that I cited, and they were very impressed actually. So these are the things that I would conclude up with boundary layer development. If you have any questions, you can just mail us or write us in the comment section. Thank you very much. We are almost about to reach 1000 subscribers. So if you like our channel, like it, share it, and do not forget to subscribe. That's it for today. Thank you.